Our next speaker is Dr. Richard Bazinet, who's an associate professor and Canada Research Chair in Brain Lipid Metabolism at the University of Toronto. He is past president of the International Society for the Study of Fatty Acids and Lipids, and Dr. Bazinet sits on several editorial boards and currently the editor-in-chief of prostaglandins, leukotrienes, and essential fatty acids, as well as senior associate editor of lipids. The overall goal of Dr. Bazinet's research program is to identify the mechanisms that regulate brain lipid metabolism and to identify the role of brain lipid metabolism in the pathogenesis of neurodegenerative diseases and neuropsychiatric disorders. Dr. Bazinet has published more than 130 papers, largely in the field of brain fatty acid metabolism, and is a co-author of the joint WHO-FAO Joint Expert Consultation on Dietary Fats and the Central Nervous System During Aging and Disease. Dr. Bazinet's presentation today is entitled Omega-3 Fatty Acid Biosynthesis, Updates and Controversies. Please help me welcome Dr. Bazinet to the stage.
Thank you, Harry. Thank you very much, Harry. Thanks, Ellen. It's great to be here, giving my first talk in person in about 2 years. So hopefully I remember how to do this, or it's going to be a long 20 minutes for all of us. What I want to do is I want to keep in the spirit of the speaker earlier, and I want you guys to look over the fence. I'm a metabolism person, and I just want to share 4 or 5 things that I think we've found that are kind of fun, and maybe you guys can think of some ideas and what to do with them. I'm going to give you the most brief background ever. It'll be 1 slide, and it's a metabolism pathway just to make sure we're all on the same page. Then I want to talk about how much DHA is actually in the human brain. For those of you who know the pathway, and we'll go over this, there's a weird step in the synthesis pathway where you become a 24-carbon molecule, and there's a little debate if that's actually a precursor or a product of DHA. And as a Canadian, I'm open to both ideas. I'm going to talk about how when you give DHA supplements that are relatively pure and EPA goes up, that's often called retroconversion, and I'm going to challenge a bit of that. It's a new technique we've got. I'm going to talk about how when you give EPA, DHA doesn't go up, but there's some really interesting things going on there kinetically. And then I'm going to teach you how to tell the difference between DHA and DHA, a fun little trick we've come across at the end that I think might have some useful applications. And a lot of this, except the unpublished data, is in this review I put out with Adam Metherall about a year ago. So here's the one background slide. And a lot of you will know this, but if you don't, here's DHA at the bottom. We've got ALA, we like to say in Canada, flaxseed and canola, 18 carbons. They come to EPA, which I'll be talking a lot about, 20 carbons. And then there's this THA step. So you get a little longer, and you get beta oxidized. Howard Sprecher showed that, and you come DHA. The other thing we'll talk a little bit about is how DHA can go back to EPA, and it's something called retroconversion. But before I get started, I just want to, answer a simple question that's been haunting me my whole career, and it's actually how much DHA is in the human brain. And I go to a lot of conferences and I ask people, ask my colleagues how much, and they'll say things like 12%, and that's nice, but 50% of this room is females. It tells me nothing about the amount of people, the amount of females in this room. You got to do this, and you got to do this quantitatively. So there were some estimates in the literature. My old boss would take a gram of human brain, figure out how much DHA was in it, and multiply it by 1,300 to get the brain. And there's a couple infant studies. So we decided to just do it. So we got half a dozen human brains in the lab. A PhD student, Scott Lacombe, who went on to do his postdoc with Tom Brenna, and an industrial blender. And we did a lot of pilot work, and this is actually really tough because we want to homogenize a whole brain, and we had to make a uniform solution. And you have to do this over and over, and we packed this with pig brains, but we got it, and we got a nice uniform solution, and we ran chromatography. And this is chromatography, so these are each fatty acids. And there's the DHA in the human brain. It turns out there's about 4 grams of it. And you'll notice a few things. There's more palmitate, if you can read these. There's more stearic and there's more oleic. That's an internal standard and that's another internal standard. And we did it 2 ways just to make sure we got this. So now we have a number, 4 grams of DHA in the human brain, which we had estimates ranging from 2 to 10. And that matters a little bit because now we can start to talk a little bit about how do you get that? You know, how much do you need to eat to get 4 grams in your brain and how much do you need to replace every day? So that's check mark number 1 done. And I want to come back to this pathway now and start talking about some of the steps. And specifically, I'm going to move into a murine model, a rodent model, and I'm going to talk about THA. Howard Sprecher, who sadly left us in 2019, really got this going. And he did a lot of studies, and I think he really convinced me that when he added that THA molecule, it turned to DHA really rapidly. But if you look really closely at his studies, he was showing that DHA could also become THA, but he dismissed it because he said that the THA levels were low and the DHA levels were, you know, the synthesis was low, but kinetically it's complicated because there's a lot of DHA in most of these cell systems, and even if you have a slow rate of conversion, if you have a big pool, a lot goes forward. And one of my colleagues, Tom Brenna, has done a lot of work where he's adding labeled DHA and he's showing it going to THA. So there's something going on here. And we decided to test this in our kinetic models in a rat with adametherol. And the key to this study was getting THA pure. Because one of the criticisms in the literature, if you look really closely, is people say they never showed the purity of their THA. It might have had a little DHA in it, and the THA might have went to DHA. And then the same group says the exact opposite about the others with the DHA. If you had a little THA in your DHA, you can't do the study. So we worked with an isotope company. It might not be that clear here, but we got THA right here with absolutely no detectable omega-3s in it. And then we got DHA with no detectable THA in it. And we infuse this as a free fatty acid into rats, into the vein. And what we measure is the appearance of the products coming out in lipoproteins. And this is how the graphs look. So here we're infusing DHA, and out comes DHA esterified. That's what we usually see. If you infuse ALA, you see ALA come out. But here, you see a little THA. So people like Tom Brenna, they're right. You know, we're putting pure DHA in, and we're making THA. When we infuse THA, this is really wild. Like I said, you infuse DHA, DHA comes out, you infuse ALA, ALA comes out, and everything's lower. But THA actually wants to be DHA. So we're infusing THA and it's coming out as DHA more than THA. This must have been Howard Sprecher's moment. You know, you put a molecule in and a few minutes later it's something completely different. It was just beautiful to see it. But there is a cycle going on here, and we can't do all the kinetic modeling, but it turns out that DHA is going to THA and THA is both going to DHA, and we've got an estimate that the rates are about 1/10, one way or the other. So if you come back to this pathway, I'll slide it over. I think right here we can draw a little arrow, you know, a cycle going on. And I just think that's fun. I don't know the full significance of it, but we were able to make some THA and make a THA ethanolamide, and we're able to show that THA products have effects in the brain. So there's probably something really, really neat going on there. Now I'm going to take a step back, and I just want to talk a little bit about a new method and a concept that we've been interested in. And it deals with carbon metabolism. And at some point, you may have remembered learning about something called C3 and C4 plants, or sorry, C4 and C3 plants. And what's important here is fatty acids are made up of carbon. Carbon usually weighs 12, but about 1.1% of it weighs 13, so it's a little bit heavier. And it turns out that C4 plants get even a little bit more carbon-13 compared to C3 plants. And that's significant because our food supply varies a little bit. And it turns out corn, which is used a lot in North America, has a little bit more carbon-13 than most of the plants in our food supply. And fish, it's not in this CAM pathway, because it's in the ocean, lands somewhere in the middle in kind of a moderate carbon-13 content. Why am I interested in this? Well, I once looked over the other fence and I read an anthropology paper. And these anthropologists, what they were doing was they were digging up pots, 6,000 years old, and they were scraping the pots to see what was in them. And they were scraping the palmitate and the stearic acid, very stable molecules, been in the pots for 5,000 years. And they were looking at the carbon-13 contents. And when the carbon-13 contents, were about -30, the units are terrible here. Geologists made this up. And what happens with geologists is they took a reference standard called 1, and then everything in the world ended up being negative relative to the reference standard. So the units are cumbersome, so I'll just talk about more or less, and we won't get into it. But when they come in at about 30, they say they're, this is C3, these are coming from ruminants, and when they come in at about -23, 25, they say, oh, that was fish. That was fish that was in the pots. And I said, well, wait a second, if they can do this in 5,000-year-old pots, we can do this in humans, we can do this in animals with the same sort of technology. And this is the technology. It's called gas chromatography isotope ratio mass spectrometry. And it's a very weird instrument. You use a GC to isolate those peaks like I showed you, and then you combust the fatty acids, and when you combust the fatty acid, you make carbon dioxide. And in a way, this machine's useless because all it does is measure carbon dioxide. It's got multiple detectors, and it's measuring the carbon dioxide coming off the fatty acids, and it's saying, do you have a carbon-13? Yes or no? And it gives us really, really high precision. Whereas I think we'll hear about other types of mass spectrometry that can measure a lot of things, a lot of diverse things. This only measures carbon dioxide, but it does it at a ridiculous precision. And here's an example of the precision. So here on my machine, I've sent 4 pulses of carbon dioxide to it, and these are the answers I've got. So you get, that's called 1%, so it's about 1.1% carbon-13. And you can see we can get down here to 100 thousandths of a percentage, and we're just starting to lose our accuracy with 802 versus 797, which still isn't that far off. So we're working at almost an unthinkable small differences in carbon-13, but because we have this really precise instrument, we can do it. And then when we look at actual fatty acids, they vary by a mile. There's really big differences in the carbon-13 content in fatty acids. So we wanted to set this up and develop a method, and Scott Lacombe did this for us. And a very simple study. We took animals and we gave them either ALA or DHA. And we got the ALA from a plant source, I think it was flaxseed, and it came in at -29, so low carbon-13 content. And we got DHA from fish at -23. And so the ALA animals only had ALA and the DHA animals only had DHA, and we let them go for 2 generations and did our analysis. And what I'm going to show you here is brain DHA carbon-13 levels. So I'm not showing you ALA, I'm not showing you brain ALA. It's always DHA, and here's the carbon-13 content of the ALA diet. And the ALA animals, if I look at the DHA, it matched perfectly, right? So the DHA in these animals came from that ALA, and it matches. When I look at the DHA-fed animals, I can tell the difference. So I've got DHA molecules here, but by looking at the small differences in the carbon-13 signatures, I can tell where they came from. They use this in sports drug testing. Testosterone comes from cholesterol. If the carbon-13 content of your testosterone doesn't match your cholesterol, you cheated, and that's it. And so that's what we're doing here. Like, who do you look like? Who's your precursor? Who's your parent molecule? So now I want to take this method, and I want to walk through a couple questions we've been able to answer. And one's, what's retroconversion? There's a few ways to do retroconversion, but the most common thing in the literature is you give a DHA supplement, which increases DHA levels, but EPA also goes up, and that's quite common. And people have ways to calculate this as a percentage of the other peak, and 10, 11% of DHA is retroconverted. But there are alternative reasons why this could be going up. So if you look at the pathway, one, you give DHA, EPA goes up, possibly because of retroconversion. I want to be clear here. You can give a tracer and you can show this pathway happens. So I can give a DHA tracer and I can show the tracer shows up in EPA, no problem. 2 is, and I don't have a reason for this, but you could speed up the ALA going through and get stuck at EPA. Or two, you could slow down EPA going to DPA and lead to an accumulation of EPA. So it's not necessary when you do this in human blood and you see EPA go up that it was retroconversion. So we did a study in rats where we, fed them DHA, EPA went up, and when we did that, what do you look like EPA? The EPA carbon-13 signature did not look like DHA. It looked like ALA, which doesn't fit with retroconversion. But we were very fortunate, and we were able to do this in humans. And I don't know if you can see it, but David Much, the University of Guelph, Caitlin, you're a former supervisor. I think I see you back there. We collaborated with him on this study. It's a very small world. And what he did was he had 3 arms in the study. One group gets olive oil, 3 grams for 12 weeks. One group gets DHA, which I'll talk to you about first, and then I'll talk to you about the EPA results. Total fatty acids, and I'm going to show you our isotope analysis. So this is how the data looks. These are plasma concentrations of the various omega-3s pre and post 12 weeks. And when you give olive oil, nothing happens, right? Nothing's supposed to happen. Olive oil is omega-9. This is how the carbon-13 signatures look. And there's the carbon-13 signature of the oleate. And again, nothing happens. The baseline levels don't change because the oleate supplement doesn't get converted into omega-3s. But then what we did is we looked at the DHA supplement, which came in here at about -27, or not very enriched. And so this is the key. When you give DHA, nothing happens to ALA, right? Concentrations in the blood stay the same. DHA goes up, which it's supposed to. But EPA also goes up. And that's what people call often retroconversion, okay? Because EPA is increasing, DHA is increasing EPA. But when we look at the signatures, and here's the signature of our supplement, nothing happens to ALA, as you'd expect. The DHA supplement happened to match the plasma levels of the DHA subjects. But importantly, the EPA signature didn't change. So if the DHA was being converted to EPA, it should have jumped up towards the level of the supplement. We didn't see it. In fact, it matches the ALA, so we think we got a backlog going on here, and the EPA is actually coming from ALA and being slowed down. So if we go back to this pathway, what we think is happening is that the DHA is stopping this. And we've got other studies that I'm hoping are going to come out this summer where we think we found the enzyme that's involved and some of the kinetics of the reaction. So often when you give DHA and EPA goes up, you change the metabolism of EPA. And I think this is probably important because there's a lot of discussion about how much EPA to DHA in a supplement and all these ratios. And this is just showing that at a certain level, DHA is going to change the metabolism of EPA and increase it. Now back to DHA synthesis. So what I've got here is I think it's a well-established, these are clinical studies where they gave up to 15 grams of ALA, EPA goes up, and DHA doesn't, okay? So you give ALA, you can increase EPA, you can't increase DHA. Some of my colleagues say that's because ALA is not converted to DHA. This is one that's more relevant. This is a study, it's kind of a subset of the reduce it. They gave 4 grams of EPA, EPA goes up in the plasma. DPA goes up, but again, no change in DHA, right? So you give EPA, EPA goes up, but you can't get that DHA to go up. And some people say that's because EPA is not converted to DHA. Well, let's go through our study, same study, and we're gonna look at the EPA supplement, which was actually quite enriched at -23. So here's the data, plasma concentrations, you give EPA, nothing happens to ALA. EPA goes up, which you'd expect goes up a lot. DPA goes up a little bit, and the DHA, no change, right? EPA does not increase plasma DHA levels. But let's look at our signals here now with our supplement up here. ALA, no effect. There's no conversion of EPA into ALA. EPA, so now we've given it a supplement. and the carbon-13 signature of the EPA in the blood is approaching the supplement level, but so is the DPA, and so is the DHA. And in fact, the DHA is as labeled as the EPA supplement. And what this means here is that while you're giving EPA, you're not increasing DHA, there's a flux going through here. And if you take a look at these subjects, all the DHA in their blood, they weren't consuming any other DHA, is actually coming from EPA. So there is conversion, it's going through quite nicely, but it's not increasing DHA. And I just think that's a different way of looking at this problem, as opposed to just saying, oh, it's not converted. It's converted, but for some reason it doesn't increase it. And I think we gotta think about why that might be. Last little trick that we can do, that I'm quite excited about, is, you know, God bless America, there's a lot of corn here, and there's a lot of high fructose corn syrup. And I'm told that they feed algae high fructose corn syrup in the States, which gives it a different carbon-13 signature than fish or other things. So we've been doing this, we've been buying algae, algal DHA from a variety of sources, and we see that in fact, the DHA is more enriched. And then so what we can do with this, and this is a murine study, we're going to take some mice, put them on a fish diet. We're going to switch some of them to an algal DHA diet. And then we've got an isotope, it's plus 88. So one's minus 13, minus 30, plus 88 as a spiking exercise. And I'm going to measure the turnover of DHA in the brain with this technique. And here's how the data look. So this is brain DHA carbon-13 signatures. The fish stays flat because that's what the animals were on coming into it. But here's the carbon-13 signature after we give the algal DHA, and they separate quite nicely. So I can tell the difference between DHA that came from algae, DHA that came from fish, and DHA that came from alpha-linolenic and flaxseed just by looking at the weight of the DHA molecule. And it's turning over the tissue nicely. Our spiked one looks like it's going through the roof, but you got to remember this only has to go to minus 13 and this has to go to plus 88. So when you actually do the percent turnover numbers, they give you the same answer, about 46 days for brain turnover. So I think this is neat. You know, if you're feeding farmed fish a DHA source, we could check the DHA in the farmed fish to say, oh, that came from algae or that came from another fish source. So we could trace it that way. So let's wrap this up. How much DHA is in the human brain? We're hoping to publish, only a handful of people know this right now. It's about 4 grams. 3.7 was the average we got. Is DHA a precursor or a product of DHA? I think the answer is both. They seem to be in a cycle, and we could debate, you know, which way the cycle is heavier or lighter. Well, DHA can be retroconverted to EPA. Sometimes we just use that word too lightly. Every time we see EPA go up, we say it was retroconversion, and sometimes it's not. Sometimes it's DHA changing the way EPA is metabolized. Dietary EPA does not increase DHA. If you want to increase DHA, you take DHA, but there's a flux through the pathway, and I just think that's a different way of thinking about it. And then, you know, how to tell DHA from DHA, and the American source is heavier. Basically, it's got a little bit more carbon-13 in it, and with high precision isotope ratio mass spectrometry, you can tell them apart. So with that, I'd like to thank my collaborators who did most of this work, especially Adam, and my multiple funding sources who, you know, I have some basic science grants that I love because I just get to do science without proving I'm going to cure everybody. And it's just the curiosity of some of this stuff that we're allowed to answer in the lab, and I get the pleasure of sharing with you. So thank you very much for your attention.